Diffusion with a generalized Robin condition. Recently, Scott Gould initiated a discussion of the Robin boundary condition on Maple primes. In a conversation with Scott about his post, I recall that in 2010 I had solved an interesting diffusion problem posted to Maple primes. My solution appeared in a Maple Reporter article in September of that year. It was interesting because it had a non-homogeneous Robin boundary condition at one end, and the inhomogeneous term was governed by an initial value problem that in turn was coupled to the diffused quantity. My solution was obtained by a finite difference discretization and verified numerically by inverting the Laplace transforms of the appropriate quantities. However, at that time, Maple had limited functionality for numerically inverting Laplace transforms, so I made do with numerically approximating the relevant Bromwich integrals. In Maple 2020, a built-in functionality for numerically inverting Laplace transforms appeared. After reviewing the work in the Reporter article, I will show how implementing the new numeric inversion tool in Maple validates the earlier approximations I had made. Table 1 summarizes the diffusion problem. Table 1 here summarizes the diffusion problem. This is the diffusion equation, the heat equation if you like. There is an initial distribution, call it temperature, 0. The left end is insulated, so there is the derivative set equal to 0, Neumann condition. This is the Robin condition on the right end. The temperature at the right end, the flux at the right end, and some driving term, non-homogeneous term. But this term is not prescribed. It's governed by this initial value problem. And the initial value problem is coupled to the temperature at the right end. So, differential equation governing F, G is a driving term in that equation and an initial value to make this an initial value problem. Well, Maple's pdsolve command will solve one-dimensional evolution equation. It does it numerically by finite differences, and it will also solve, again numerically, initial value problems for ordinary differential equations. But there's no provision for the kind of coupling that takes place here, but the problem does yield to a simple finite difference scheme, and that's what we're going to show below. In addition, this problem in this table is linear, it has constant coefficients, so it all yields to a Laplace transform solution. So capital G, the transform of G, and capital F is the transform of F. We can find those easily, but the expressions that you end up with are sufficiently complex that you can't invert them analytically. So we try a couple of inversion techniques. Brute force numerical evaluation of the Bromwich inversion integral, and a more sophisticated numerical inversion scheme along a deformed contour for the Bromwich integral. And then finally, what we want to take a look at is this new functionality that Maple has for numerically inverting Laplace transforms. Well, let's get started with the solution. We'll need some initialization steps, so I'm going to need something out of the plots package. I'm going to change the imaginary unit from uppercase I to this lowercase I, which looks more like what you see in textbooks, and then the intrans package so that I can access the Laplace transform command. Let's say a word or two about the Robin boundary condition. In general, the condition is of this form. U is the quantity being diffused. So you have U here. This is the normal derivative, and this is the location where this is taking place. This is a driving term. Typically, it's a known function, but for us, in this problem, it's not known directly. A and B are constants. In this table 1, the problem there has A and B equal to 1, and that's our x is 0. So this is a 1 here, and this function is not known. We have to calculate it. So let's look at the finite difference scheme that will help us solve this problem. So very simple approach to the differencing. You find this any standard numerical analysis text that treats partial differential equations. Step size in x, 1 over n. Step size in time is a multiple of that x step size squared. And this multiple is restricted, and that restriction comes from the stability requirements. And eventually we picked lambda to be a half. We have 10 points in the x direction. That makes the step size in time 0.005. So xn, you're discretizing in the x direction, n steps of size h sub x. Time steps tm, we'll use m for the time steps, h sub t, where you figure out what h sub t is here. This is what we're going to end up using. Simple forward differencing. So this is simple forward differencing for the derivative on the left, which is a time derivative. This is the x derivative, so it's a second derivative. And this is the differencing for that second derivative. If you put in the value of lambda, where you're going to have this h sub x squared and this h sub t, this is going to go up, this is down, so you're going to get a lambda. And you isolate this g. This is the one you want to isolate because it's next one time forward. And it's given in terms of these previous values, m, 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 their previous values. So this is the computational molecule that shows what this equation implies. At time m, it takes 3 x values to compute one new value in time, but you can only get it at the center point of this triplet. If you are at an end, then you will need a value to the left of this last x, and if you're at the right, then you need a value to the right of the last x, and so you got to figure out how you're going to get those outside values. Well, you get that from derivative conditions. So at the left, when n is 0, you're looking at this where the n, the counter, is at 0. You need a value to the left of that, which is what this symbol represents. And so look at the homogeneous Neumann condition on the left. You need derivative set equal to 0. So a simple derivative in the x direction at time m is homogeneous, so that's equal to 0. That says these two terms are equal. This value at the outside the left edge is equal to the value at the left edge. On the right side, on the right end, this is what you're looking at. That's what this equation tells you to look at. So on that side, you have the Robin condition. So you discretize the Robin condition. This is the function value. This is the normal derivative, x derivative, and it's equal to a value generated from that function f that we don't know yet. So we're looking for this value right here. So we'll solve this equation for that value right there. It's equal to this stuff. So then you can put that up into here, and you have this expression for stepping forward in time. But we still have to calculate this Fm. So what was that equation? It was F prime plus F equals G. So simple differencing for the derivative. New value of F is what you solve this equation for. And so that is equal to this stuff. That's how you step forward with F. And you need an initial value, and it's clearly 1/5. And after a couple of numerical experiments, I discovered that I didn't need to go beyond t equals 4, and m, therefore, was 800. And the actual calculations are summarized in Table 2. Table 2 summarizes the calculations that we have to perform. So we need the number of steps in the x direction. This is lambda. L is easy to type in. Lambda hx, spacing in the x direction. Ht, spacing in the t direction. This expression appears several times, so I gave it the name C. This appears several times, so I gave it the name R. And M turns out to be 800 under our set of parameters. This initializes G at time 0, right? That's time 0. So all of those nodes across the very first row are 0. And here's where all of the action takes place. We set F0 to be 1/5. And this is a double loop, right? There's a 4, and an end. So here we have x equals 0. So we are marching ahead in time. See, m is what's changing, so that's the time step counter. And this gives us what's going up the left edge. Then this is marching up in time, and this is that 3 values gives you a new one. And this is up the right edge. This gives you what's happening on the right edge. Then that gives you G. If you have G, you can then compute new values for F, and f is a function of t, so you have fm, and there's where g feeds into the definition of f. So having generated all the data points, 8811, draw two figures. One where I draw the solution surface, and one where I draw a graph of f of t. Now, the actual code that draws these two graphs is hiding behind the cell, and I'll show you once how you can get to it. Now, I do it from the keyboard, but let's show you. It's Format, Table, Properties, and you see that Show Input. Check that so that the input shows, and you can see here was the code that generated this graph using surf data, and here's where I make points, and surf data then takes the points and draws the graph. And I did the same thing back here. And so you can see what the solution surface looks like and what f of t looks like. So let's move on to the solution by Laplace transform. So first we've got to get some Laplace transforms. And I've got that summarized here in this table. So we take the transform of the heat equation, or diffusion equation, with respect to t. Subscripts indicate partial derivatives. So this is the transform of partial with respect to t. So you got an s and the value at t equals 0. And on the right side, you have the transform, but the two derivatives with respect to x can be applied outside the transform. G at times 0, that's this number here, is 0, so this simplifies, this term drops out. This is an ordinary differential equation in x, so it's got a simple solution, exponentials. The homogeneous Neumann condition on the left reduces this to this, so A equals B. So we put an A here and we factor out the A, and we've got a statement of the transform of G, but it's got this A in it. And we're going to have to get some boundary data to figure that out. So now we turn our attention to uh, the equation for F. Now, if you recall from the introduction, the initial value problem for F looks like this. It's F prime plus F equals G. That's the coupling that takes place in the Robin boundary condition. So I've just repeated that here. And then I take its Laplace transform. That's a function of t, so I take it with respect to t. So this is the derivative term, f at 0. And then this comes from here. And this comes from here. Now we know that the f of 0 is a fifth, so we put that in, and then we solve for capital F of s, the transform. So we now have the transform for f. But because we don't know a, we're going to have to work harder. So now we take the transform of the Robin condition, and here's the statement of the Robin condition. So we take its Laplace transform. You can see here I'm going to get capital F. From this term, when I transform, I'm going to get here G1S. And here the derivative sits on the outside because I take it with respect to t, G sub x. So we have something that we can put in for F from here. So we put that in and simplify. And we now have g sub x is equal to this. And we still need a way to calculate this a before we can say we've got to transform capital G. Now, to make further progress here, we are looking at this equation and we are saying to ourselves, we have an expression for G that we can use here and here and perhaps thereby calculate what A is. And so that's what this next statement says. Remember that we have this statement for G, which is this one here. We're going to use that to determine A. And now we have a series of these cells that are colored in yellow. And the reason for that is each cell hides some maple. And I'm going to explain the math. And if I've shown you how to see what's going on in the hidden cell, to get the table properties and click the show input option. So what is the math? The math over here is G sub x. So you take the derivative with respect to x, and that's where this extra square root comes from, and you evaluate it at x equals 1. That's why this has an x, but this does not. So that's the left-hand side. On the right-hand side, you see that 1/5, and see the s, and this is g at 1s computed from here. And so we have an a here and an a here, and we're going to use this equation to solve for a. Now it turns out, and the Maple code for doing this, a is pretty complicated. It's not a simple expression for a. So we now know g, and we have this expression for f. The expression for g is going to be this, because we've gone back here and we've put in this big mess for A. So now we have G and we have F. And it turns out that if you do a little mapleizing, you can compress this down a little further. You got a hyperbolic cosine, hyperbolic sine, hyperbolic cosine. And then that means we can write F from here in terms of hyperbolic sine and hyperbolic cosine. And the maple for getting these two expressions now are hiding behind these cells. Well, having gotten these expressions for the transforms and realizing that we can invert these things, so we try to get some information from them, check that information against what we know to be true, or can figure out what's true, just to get confidence that we haven't fallen off the deep end of the wharf here. So let's try to extract some information from these expressions or the transforms. Theorems that apply here are typically called Tauberian, in contrast to abelian theorems, which go in the opposite direction. So you can extract initial and terminal values for these functions from the Laplace transforms. So if the function is of exponential order, so you're assuming that you have something that's of exponential order, and h is its transform, then the limit as s goes to infinity of s times that transform is equal to the limit of the time function as t goes to 0 from the right. So let's try that here. Let's look at the limit s goes to infinity of s f. You get 1/5. That looks good. And if you do it for g, you get 0, and that looks good. So both initial values here are recovered. There is a final value theorem that says the limiting value of a function of t can be found by letting s go to 0 in its transform, or s times its transform. Well, h has to be bounded, and its limit at t equals infinity has to exist. Then that limit is given by the limit as s goes to 0 from the right of s times the transform. And that's what we've done here. S goes to 0, S goes to 0, SG, SF, and each of these final values are 1/10. And if, when we can somehow or other invert the Laplace transforms, if the limiting values as t goes to infinity for these two functions are the 1/10 that we see here, we have some uh, confidence that we're on the right track and we're doing things correctly. So now I'm going to attempt some form of numerical inversion of these transforms. And I began with the use of the Bromwich integral. This is the inversion integral for a Laplace transform. 1 over 2 pi I, because almost everything in complex variables has a 1 over 2 pi I in it. Here is the transform, e to the st, as opposed to the transform, which is an integral with e to the minus st. Gamma is the path for this line integral. It's a vertical line, so that's why you have IY, because you're integrating up and down a vertical line. And C is along the real axis, and it has to be far enough to the right so that H is analytic in the right half plane to the right of C. And that's what all of this stuff is saying. And H has to be well behaved, uh, in which case then you can invert using this Bromwich integral. But the Bromwich integral is very, very difficult to evaluate. In my AEM book, uh, when I talk about this, I do a couple like 1 and t squared, but after that the integrals just become impossible. Now, want to look at the behavior of f and g. So I look at its absolute value. You got these two spikes, but the spike is to the left of 1. That's for f. And for g, look at its absolute value. You got two spikes, and the spike is to the left of 1. So if I pick c to be 1, this integral applies. So let's see if we can implement this Bromwich integral, but evaluating it uh, directly numerically. Typically difficult to do. The integrals oscillate out to infinity, and these are a nightmare to evaluate. On the line 1 plus iy, the integral that we have to do for inverting f will look like this. We look at the real part. It turns out to be an even function of y. The imaginary part is odd in y, so that's going to drop out when you integrate minus infinity to infinity. So we're now confronting this integral. And because it's even, we can go 0 to infinity instead of minus infinity to infinity. Well, this is a nasty thing. So we look at Maple's repertoire of numerical techniques for such integrals, and we look in its list of what it grabs out of the NAG library, and it has this method designed for oscillating integrands on a finite interval. So we're going to take a finite number up here and we give it a try. I got some points, I got some values, and I drew this graph. The way I drew the graph, you can see what the code was. The code is hiding behind this table cell. I've shown you how to open up those table cells. From the keyboard is on a Windows machine here. It's Alt R A P that brings up the table properties. If I check Show Input, you can see here. Here is the method of integration. This is the stuff I'm integrating. I made a function so I can get multiple points. Then I send that function to the plot command. I believe I said limit the number of points here. You can see it's uh, kind of broken line here. It's not smooth, but it has a limiting value of 1/10. Starts at the right place and it tends to the right place, and I kind of like that because it conforms to the previous information I got from uh, the finite difference scheme and from the Tuberian theorems. I used 10 points for that. It took time. It takes time. You got to be patient, and then you do the same thing for the surface. Let's take a quick look at what we did for the surface. Uh, Alt RAP brings up the table properties. Do a show, and here you can see this is the thing I want to invert. I make the substitution, the appropriate substitution for S going up the vertical line. Make a function so I can make some points, and I use surf data to draw a graph of those points. Well, that surface seems to look like the surface I got when I did the finite difference scheme. And the limiting value here, 0.1, appears to be 0.1, conforms to what information I have gathered before. Well, now it's time for a little bit of research in the literature, and you find references that tell you how to deal with this Bromwich contour integral. And here's one that I reference that I found. I'll show you in a minute what it is. Deform the contour, and you end up with this integral for the inversion of a transform f. You need to define these quantities. S of theta is this. Sigma of theta is this. And so you have the real part of an e to the t s of theta, f of s of theta, and then here's where the sigma appears, integral d theta. There is an r, and r is 2m over 5t. Where do you get these numbers from? M is the precision of the computing device, and the relationship between r, m, and t is empirical. And it was designed to allow for an increase in the device precision as t increases. So I fooled around, I played around, and I said, okay, I'm going to let t go from 0 to 5. That will give me r equals a fifth. Default 10 digits in Maple turn out to be enough, and it allows us to use Maple's built-in integrator rather than the trapezoid rule that this reference recommends or suggests. So I tried this, and I got a graph of t down here, graph of f down here, that looks right. It agrees with previous versions of this graph. Let's see if there's stuff hiding. Alt RAP. Is there stuff hiding behind here that shows us what we did? So you can see here I define S, and here, that's this guy S, and here's sigma. The real part, that's this part. Make a function of what I want to integrate. Right, there's int. Make a function out of it, and I make some points. This is the initial point. Bunch of points in between. 20 of them in between. I draw a graph. This is what I got. Okay. And I did the same thing here for G. It takes some time. Um, I think I used 110 points for this guy. And you want to take a look at what's behind here. Alt RAP, show input. And you can see here's your real part. Make a function to int, so each call to that function does an integral. I make some points, and then use surf data to plot those points. Get a graph that looks like the uh, appropriate shape of the solution surface. So now I want to show you the new functionality in Maple. And that's the real reason for going back to this previous work to compare what I had to do in the past to what one can now do in Maple. Where is this information hiding? It's right here. Updates, Maple 2020, integral transforms. This information is not available anyplace else. There's never been moved to its own help page. So you have to go back to this update page, and then down here to numerical evaluation. This is the information that tells you how to use this stuff. So I'm going to make use of it here. Uh, f of s has a name. I think I used fs, hiding in one of those yellow cells. I'm just recovering it, giving it the name f. That's the Laplace transform of f. I did the same thing for g. Give it a unique name. Let's call it g. How do you work this stuff? You apply the inverse Laplace transform command, inv Laplace command, to f, and you apply it to g. You apply it to f. I call it if, or inverse f, ig inverse g. This one got split because of that plus sign right there. So you have these two things on the screen. Leave them there. If you want to evaluate the inverse Laplace transform at a particular point, you would do something like this. Eval, which is a substitution, if, that's this thing, at t equals 1, and then call eval f on it. So that gives you the value of the function little f at 1. How do you draw a graph? Eval f, this stuff here, and send it to the plot command. T equals 0 to 5 is interpreted in the course of constructing the graph. So the substitution is being made into if because of the plot command. I fix the view. I limited the number of points to 10 so that I wouldn't be waiting all day. And the shape of the resulting curve of 10 points is what we had seen several times before. It looks pretty good. I do the same thing, or an equivalent thing for G. I wanted to time this to see how long it took. So you do the same uh, call to eval f on IG, and the plot command is plot 3D. Range on T, I went 0 to 3, X 0 to 1. I limited the grid 10 by 10, which is limiting the number of points. I have the orientation so I don't have to twiddle this thing around, so you can see that the shape of the solution surface is conformable to the previous graphs of the solution surface that we got before. And I would like to know how long it took in real time for me to wait for this graph to be drawn. So this is the way you do it. You establish the time, and then you take the new time and you subtract off the old time. It turned out to be 15 or 16 seconds. I think this is a considerable improvement over what I had to do prior to the appearance of this numeric inversion technology within Maple. Now, the last thing I want to show you would be these two references that I made use of. This is for the numeric evaluation of the Bromwich integral on a deformed contour. If you click here, you will automatically download a copy of the paper. My experience is that the click automatically downloads. This reference is the one I believe was used by Maplesoft when they implemented their algorithms for numeric inversion of Laplace transforms. And if you want to see the full paper, you can click here, but then you've got to find the appropriate spot to do the download. There are three methods that Maplesoft implemented, and it picked one as a default method because it found that it was better. If you look back at the place here where the information for this integral transform numeric inversion is given in Maple, you will find additional information that shows what the three methods are and how to implement each of those, any of those three methods separately. I poked around with it and I said, you know what, the default method works fine, and I just went with the default method. So uh, that was the surprise to me to find that the struggle that I had years ago trying to solve this problem is now a little easier with the new stuff that Maple added.